Good morning. Let's see. Need to find the problems we were working on yesterday. Well, let's see. There it is. Okay. I know I printed those things off just yesterday in all the confusion. I guess I'll print them again. And we'll switch views here to that. Okay, should be looking at a bunch of numbers on a piece of paper right now, which you can ignore because that's the other class. And I may have time later today to grade your test. We'll see. Yesterday was just insane. I gave tests at 1, 3, 5, and 7, and actually had 2 classes going at the same time with taking tests. And the engineering physics tests were lasting 2 hours each, and so the one that started at 7 didn't end until after 9, and it was just kind of a crazy day, but that's all right. Yesterday, we had just introduced Newton's second law, and that was about as far as we got. And I pretty much just wrote something there that the acceleration of an object is the net force acting on it divided by its mass. And mass is a measure of inertia. It's something that we put on there. Oh, if I didn't mention it yesterday, I have got the new, let's see, this class is sapling homework posted. And I've also, this afternoon, I'll be posting the lab assignment, and this will be a team lab assignment where you'll work together in groups. And so the first thing to do will probably be to contact each other and figure out a time when you could have a mutual Zoom meeting. And when I send out the emails to you, assigning you to the different lab groups, I'll also send a Zoom meeting address that's just for your group. And so it's someplace where you could go anytime you want and talk to each other. And I'll try to figure out a way to make each of you like a co-leader of the group or something like that. That way you can share your screen, and like if you're working on a piece of paper or something, or if you're meeting via Zoom, you could use your camera and just show a piece of paper when you're trying to work together. First thing you'll do is try to figure out the initial velocity of the projectile. So we'll see how that works. But anyway, we've got this net force divided by the mass, and something that's challenging and that will show up in an awful lot of the Newton's second law problems is figuring out just what that net force is. And remember that forces are vectors. And so if you've got a force 1 that's pointing one direction and a force 2 that's pointing in another direction, you somehow have to figure out how you're going to do that. And the subject of next week's lab will be adding forces, and so you'll get a lot of practice at that, but we'll talk about it a bit today. There's also a way we have of organizing our thoughts about these things, and I have a way that I tend to do problems, and something that I almost always start with is a sketch of the situation if I'm not given that. And so I'll try to make a sketch. If it's an inclined plane, I'll draw the inclined plane, and if it's a box sitting on the inclined plane, I'll draw the box and stuff like that. Maybe write the letter M on it to signify that it has a mass. And then there's something we make called a free body diagram. And a free body diagram is just a way of showing the forces. And when you make one, you start off by just drawing a dot that represents the object, like the mass or something like that. And then starting on that dot, you draw forces that are acting on the object. And almost always the first force you draw, or the easiest one to draw, is one that represents the weight of the object. And remember, if we can solve this thing for the net force, F net, okay, and again, or just any old force, a force could equal mass times acceleration. Okay, well, if you have a mass and you drop it on the Earth, we know what the acceleration is going to be. It'll be 9.81 meters per second squared downward. And so one of the forces, and we can call that the force of gravity, will equal m times that acceleration. And this is just the magnitude of the force. I'm not indicating the direction of it yet. But for much of what we're going to do this quarter, this will be the weight of the object. It's the force of gravity pulling down on the object. And that force is acting whether it's accelerating or whether it's at rest, whether it's sitting on a tabletop or just there in the air. That'll be it. And that's the weight of the object. And so when we make a free body diagram, often the first force that we draw is just going to be mg. And here I write it as a vector. And so I'll show, put arrows on the things to indicate that they have that particular direction. And that's what we try to do on the free body diagram. The dot represents the object. The arrows will represent the forces, and I try to make sure on the free body diagrams that the arrow points in the correct direction for whatever the force might be. And so that's as far as I'm going to go with that right now, but those will be things that we do. Something I didn't talk about yesterday is what kind of units we're going to use for force. And we're going to stick with metric units for the most part, but for the metric system, the units of force are going to be units of mass times units of acceleration. And so our mass units are going to be kilograms. Grams also work, but the kilogram is the accepted unit of mass in the metric system. Now, K means 10 to the third, so it's actually 10 to the third grams, but the particular combination of kilogram is what most of the metric units are defined in terms of. And so this G here means a gram, not the acceleration due to gravity. So be a little careful, but that's our unit of mass. And then acceleration, we've always had meters per second squared. And this particular combination of units shows up so many times that it's been given its own name and abbreviation. It'll be kilogram meter per second squared. And that particular combination of units is called a Newton. And in the metric system, whenever a unit is named after a person, writing out the unit, it's lowercase, but the abbreviation for the unit will be uppercase. And so we will use a capital N to stand for a Newton. And those will just be what we measure the force in. In the American system, the unit of force is a pound, and the transfer between the two, 1 pound is equal to 4.448 newtons approximately, or 1 newton is equal to 0.22 something or other. I can't remember that one very well. I think it was on the unit conversion problem on your test, maybe, or one of the practice tests. But anyway, 1 pound is about 4.5 newtons, roughly 4.448. And so, interesting thing, in countries that use the metric system, when you get your weight, they don't actually give you your weight. They give you your mass in kilograms. And I suspect there's a reason for that. And let me show you. Let's suppose somebody weighs 180 pounds. And so that happens to be their weight. Their weight in newtons would be, if I multiply by this conversion factor, 4.448 newtons per pound. And that'll end up being a fairly large number. Yeah, it would be about 801 newtons. Okay, nobody wants to weigh 801 of anything. And so I've got a suspicion that the reason in metric countries they don't use newtons for the weight of people is because of that fact, that a newton is just a, roughly a fourth or to a fifth of what a pound happens to be. So it's not that big a unit of force. Now, this would be the weight of somebody on the Earth. We could figure out what their mass happens to be based on this, because this will equal mg. Okay, and we know what g is. So if we solve that for the mass of that person, mg, we'd have 801 newtons divided by g, which is 9.81 meters per second squared. And a newton, remember, it's a kilogram meter per second squared. So I'll write it that way here. Although sometimes you can just keep that in your head. Meters per second squared, 9.81 meters per second squared. And the meters per second squared divide out, and you end up with whatever that number is divided by 9.81. And I get about 82 kilograms. Okay, so a 180 pound person will have a mass of 82 kilograms. Now, yesterday I said that that mass depends on the number of protons, neutrons, and electrons in their body. If you go to the moon, those numbers of protons, neutrons, and electrons aren't going to change very much. You would still have a mass of 82 kilograms. If you go to Mars, depending on how much you ate on the way, you should still have a mass of about 82 kilograms. If you could somehow instantaneously transport yourself to Mars instead of spending more than a year there as our current rocket flights, getting there as our current rocket flights do. Anyway, your mass doesn't change as you go from place to place, but your weight will, because the acceleration due to gravity is different in different places. I think we did a problem on the moon where we had acceleration due to gravity of 1.61 meters per second squared. We could figure out what the weight of this person would be on the moon. On the moon, the weight, that's a lowercase w, which is just mg, is going to equal those 82 kilograms times 1.61 meters per second squared. And that weight would equal only 132 kilogram meters per second squared. Those are newtons. Okay. Well, now we can figure out what their weight would be on the moon. And well, that is their weight in the metric system, but we can figure out how many pounds they'd weigh on the moon. So if I multiply by 1 pound over 4.448 newtons, the newtons will divide out and I'll end up with pounds, and it's not going to be much. It's about, well, closer than anything else. It's only about 30 pounds. Okay, a 180-pound person on the moon would weigh 30 pounds. And I can't remember why I happened to see this yesterday, but I saw some film of astronauts on the moon, and they were having to wear these huge air circulation systems to provide them with breathable air, because there is no air on the moon, and their spacesuits already weighed a bunch. But I think the total weight of what they had was about 50% of their own weight on Earth. It might have been more than that, but so it would bump a 180-pound person up to closer to 300 pounds. But you divide that by 6 and you're down to 50 pounds, and that's what their weight was on the moon. And these were grown men who had traveled from the Earth to the moon, and suddenly their weight was just a fraction of what it had been on the Earth. And they were bouncing around on the moon, having a good time. Sometimes they'd fall over, and there was this one film of this guy who'd fallen onto his front, and he was actually able to push off with his arms and raise himself back to a standing position, because his arms were strong enough to completely launch him off the surface of the moon and go back to a standing position. That was kind of neat. So that would be fun to do. I don't think it'll be affordable just yet to travel to the moon. Probably a few $1 million per person, and not going to happen for me. But anyway, that's something that would happen on the moon. All right, we've just started to explore this acceleration equals F net over m and the other things. So let's start moving along in that direction. And I just printed those. Where did I put them? Wow, I've got lots of hard problems to do, but you don't want those. Oh, here we go. Well, let's take a look at problem 10 here. I think these were straight out of your book, if I remember right. I'm not positive. We have a rock that's thrown straight up. What is the net external force acting on the rock when it's at the top of its trajectory? Okay, well, in general, now most of the time we ignore air resistance, but if we imagine like when the rock is on its way up, the forces acting on the rock, so this is its velocity at some instant, is on the way up. The forces acting on it, if it's near the surface of the Earth, or if it's on Earth, basically, one force for sure is mg. Just because something is in the air doesn't mean that force goes away. It's always there. In fact, that's what makes it accelerate downward with 9.81 meters per second squared. Now, if it's on the way up, it may also have air resistance acting on it. And air resistance is always opposite the velocity. No matter which direction something is going, the air resistance will be opposite that. And so you might also have the force of the air. Now, we are going to ignore the air resistance almost all the time, but it would also point in the same direction as the weight does on the way up. But when it's at the top of its, at top, it has no velocity. It stops for an instant. And so the air resistance goes to zero when that's the case. And so at the top, the only force acting is the weight. And because the acceleration is equal to the force, the net force, which is the only force here, divided by the mass, and I could put arrows on these things, this will just end up being mg on top and m on the bottom, and the m's divide out, and you end up with the acceleration equaling just the acceleration due to gravity at the top. If this force vanished at the top, then it would stay up there. If there was no force acting on it when it was at the top of its trajectory, it would stay there. It'd be at rest or continue whatever motion it had going sideways or whatever, but you wouldn't have it following in a downward arc to come back. So that gravity force does not go away. And we'll learn a little later in the quarter, the gravitational force that's on astronauts in the space station or anything like that is almost exactly what it is on the Earth's surface. Well, not exactly. It's 90% of what it is on the Earth's surface. So a 100-pound person on Earth would have a 90-pound force on them when they're in the space station. But they look like they're weightless. They happen to be in a state of free fall is what they're doing, and so is the space station. It just happens to be going sideways so fast that it doesn't hit the Earth, and they're doing the same thing. All right, let's take another one of these. Describe a situation in which the net external force on a system is not zero, yet its speed remains constant. This may be a little hard to understand. We haven't studied this type of motion yet, but let's imagine that, well, shoot, I don't know where I put my circle drawing gizmo. Oh, this one works. If I can get a good enough hole in the ground here. That's not going to be a very dark circle, but we'll let that one represent the surface of the Earth. And then okay, those may be too faint to see. Now they're sort of visible. So this represents the Earth, and there's the radius of the Earth. And then we'll imagine this is the radius of an orbit. Okay, that this might be a satellite that's orbiting the Earth. Okay. Now, this is a situation where the net external force on the system, the satellite, is not zero. At any given instant, they've got a downward force on them that's equal to their weight at the altitude they happen to be at. It'll be 90% or so of the weight on the Earth, depending on the height of the orbit. But it's not zero, but the speed remains constant. And that's because they have a sideways speed, and they put the satellites into orbits so that, and that's something we control, but they put them into orbits so that the Earth's gravity acts on them just enough to bend their path, but keep them at the same altitude above there. And the speed necessary will depend on what the altitude of the orbit will be. And we can calculate all of that ahead of time before they're launched. And so you put them at an appropriate speed for the orbit they'll be in. And so that speed will remain constant. And all the gravity does is cause them to travel in a circle instead of pulling them straight down. So that's something that can happen. Let's see, if a constant non-zero force is applied to an object, what can you say about the velocity and the acceleration of the object? Well, here's what we know. The acceleration of an object is going to be the net force divided by the mass. And if the net force is a constant force and non-zero, then it will have a constant acceleration. And acceleration will equal the change in velocity divided by the change in time. Now, we just looked at a situation where the net external force was not zero, but the speed remained constant. The change in velocity could be speeding up, slowing down, or changing direction. And so we can't say for sure that they're going to be speeding up or slowing down because they may be traveling in a circle. But we do know that the rate of change of velocity will be constant in time, and so will the acceleration. Anytime you divide something by time, you get the rate of that something. And this is the change in velocity. So dividing it by time gives us the rate of change of velocity. So that's what we can say. However, let's take that to the situation where maybe that net force is in the direction of the direction of the velocity. So let's suppose that at some instant, here's the velocity, and that happens to be the direction of this constant non-zero force. Well, in this case, then, the acceleration will equal that net force divided by the mass. And if this is constant, the net force is constant, then the acceleration will be, and we'd be able to say that the velocity will equal v naught, whatever it was initially, plus that acceleration times time. And so then we could deal with a constant acceleration equation. And if everything is in one direction, we could take off the arrows and just say, all right, this way is positive, that way is negative. Then we could just write this as an equation that looks like this. And that was the first unit we had where we dealt with constant acceleration situations. So that's something we could say in that case. And if the force happened to be opposite the velocity, then we could say it had a negative acceleration. So if F is opposite V, then we could say V is going to equal V naught minus AT. You would get a negative acceleration in that case. So, okay, let's try to actually do something where we'll plug numbers into things. Here we have a 63 kilogram sprinter starts a race with an acceleration of 4.20 meters per second squared, which is quite a bit actually. I certainly couldn't accelerate with that rate. Let's see, what is the next net external force on him? Okay, well, this is a case where we know what the acceleration is ahead of time, and we know what the mass of the object is. So it's just going to be F equals ma, and the net force, this will be the net force, will equal that. And so 63.0 kilograms times the 4.20 meters per second squared. And this is about as straightforward a problem as you could get. Just plugging and chugging on here. And I get about 200 and, is that right? Yeah, 265. I can keep that many significant figures. And kilogram meters per second squared, that's newtons. So have that. This is one nearly as straightforward. A cleaner pushes a 4.50 kilogram cart, so we know the mass, in such a way that the net external force on it is 60.0 newtons. Oh, we also know the force. Calculate the magnitude of its acceleration. So here we've got mass, here we've got F net. And so when that's the case, you solve Newton's second law for the acceleration, and that's just going to be F net over the mass and 60.0 newtons divided by 4.50 kilograms. And remember, 1 newton is equal to 1 kilogram meter per second squared. So that's a kilogram meter per second squared, and the kilograms divide out, and whatever 60 divided by 4.5 happens to be. And I can keep 3 significant figures on here because I've got 3 here and 3 there. So I get 13.3 meters per second squared is what the units would end up as in that case. Oh, I just thought of one of the problems that was in the pile from yesterday. And it's a good one. It's one that I've assigned before, and people wrestle with it, even though it's not as difficult as you might think. And maybe I'll just call it up here and we can look at it and think about it here. Nope, not that batch. Okay, yesterday we did Joel, or whatever his name was, Joe Cool with his fuzzy dice. But this one, oh, I don't know what I'm sharing my screen with right now. Yeah, we'll just do it to screen 2. Okay, so here's the question. What is the net force on a 50,000 ton, and that's a TONNE, ocean liner sailing due west at a constant speed of 7 knots? Well, let's see. First of all, what in the world is a ton with a TONNE? It happens to be a metric ton, and it's 1,000 kilograms. And so we'd have to know that, but it turns out we don't have to know that because it's asking the net force if it's sailing due west at a constant speed. That sounds like due west, that sounds like a straight line. Constant speed of 7 knots. Oh, good grief. We'd have to translate that into meters per second, which isn't going to be easy, except we don't. Any idea how to deal with this?
Wouldn't acceleration be zero because it's just constant velocity?
Yes. Yeah, it's got a constant velocity. It's going in a straight line at constant speed, so there is no acceleration. And remember, acceleration is the net force divided by the mass. If the acceleration is zero, it doesn't have a mass of zero, but the net force has to be zero. So, because it has no acceleration. And how could that be? Well, the propellers of the boat would be pushing on the water with a certain force. The water, in return, we haven't gotten to Newton's third law yet, but it will be pushing on the boat in the opposite direction. But then there's water resistance from the water that the boat is trying to push through, and those things all add up to zero. And so you end up with no net force on the thing. It's just using its propellers just enough to overcome the resistance of the water for it moving through there. So it's going at a constant speed. And it's kind of a trick question, is what it happens to be. Here's another question. This is kind of related to Newton's first law, but what evidence can you give to show that there must be a force acting on an orbiting satellite or a moon or a planet? Well, if there was no force acting on a satellite or a moon or a planet, what would its motion be? It would keep doing whatever it's doing, okay? Which in this case, you have to look at it at some instant. At some instant, an orbiting object has a velocity in a particular direction. And if there was no force acting on them, they would continue to move in that direction forever. So going back to drawing a circle here, I can shrink this one down. An object in low Earth orbit, for instance, is going, roughly 17,000 miles an hour, which is a pretty good clip. So if this is the Earth, and then we just draw an orbit for something that's orbiting it, okay, let's suppose the satellite is there at some instant. Its instantaneous velocity at the instant it's right there is in a particular direction, and that would be the direction of its velocity. The velocity is always tangent to whatever line something happens to be traveling along. Okay, so 17,000 miles an hour, if there was no net force acting on it, in 1 hour, it would be way out here, 17,000 miles away. But it isn't. It keeps orbiting. So there must be a force acting on it. Otherwise, it would just travel in a straight line. And they don't travel in straight lines. They travel in curved paths. Now, this was a big break for people to have to start thinking that when Newton came up with this first law, and Galileo actually did, but the idea that it took a force to change the motion of something or to keep it moving, was a tough thing, especially the idea that it did not take a force to keep something moving. It took a force to change the motion. And all of a sudden they had to start thinking, well, maybe there's some force that somehow acts through the vacuum of space that makes the Earth travel in a curved path around the sun, or makes the moon travel in a curved path around the Earth. And this was a hard thing to come up with. And actually, Newton wasn't so crazy about it. In fact, they referred to this idea as a crazy action at a distance. That's what gravity, how Newton talked about gravity, or other people talked about gravity. I don't think Newton used the word crazy, but he sort of backed off and he said, I make no hypotheses about how this force acts, but the moon behaves as if there is a gravitational force from the Earth acting on it, and the planets, as they orbit the sun, act as if there was a gravitational force acting on them. And so that's where Newton's law of gravitation came from, and that's something that we'll get to here in a little bit. Well, we have introduced Newton's first and second laws, and we're going to do a lot more with that second law of motion, but I want to present at least the third law of motion and get you thinking about this. And this is one where if I start off with the wording going in one direction, I'm guessing more than half of you could probably finish it off, but I'm going to ignore that way of stating it from here on out. All right, and here's the way that I'll start off stating that thing. This is the way it is often stated. Okay, for every action, can anybody rattle off the rest of that? Not a brave bunch today. What you often hear is there is an equal and opposite reaction. Okay, well, what's the action and what is a reaction? People will try to use Newton's third law to justify all sorts of stuff. They'll say, well, the stock market went up last year. It's going to go down this year. That's just Newton's third law. Or somebody will say, he shoved me. I had to punch him. That's just Newton's third law. Well, you could maybe apply Newton's third law to some of the situations there, but Newton said nothing about the stock market. They didn't even have a stock market when he was living in London, or if they did, he wasn't part of it. What Newton's third law says is this, and this is a better way of thinking of it. If one object exerts a force on another, the second object will exert an equal but opposite force. It's long. On the first. And to this, you might add, forces are interactions between objects, and they always occur in pairs. Now, those pairs of forces happen to be acting on different objects. So if we let this be object 1 and this be object 2. They don't have to be the same size or anything, but this is the force of 1 on 2. Well, according to this, object 2 will exert a force on object 1. This is the force of 2 on 1. And these are equal forces. That means equal in magnitude, but they're opposite in direction. And so that's what the equal and opposite part has to do with. The forces are equal in magnitude. It's easiest to think of if you just imagine here's a positive charge here, and here's a negative charge over here. Just simple, basic atoms or something like that. Maybe this one's positively charged and this one's negatively charged. Okay. Those two forces will attract each other. The positive thing will exert a force on the negative thing, pulling it in this direction, and the negative thing will exert a force on this thing, pulling it in that direction. And those forces will be equal in magnitude and opposite in direction. Well, suppose you've got something sitting on a tabletop, like my glass of water here this right now, okay, which you can't see very well, but the tabletop is exerting an upward force on that cup of water. The cup of water is exerting a downward force on the tabletop. That's happening because of zillions of interactions between charged particles that attract or repulse each other. In this case, they'll be repulsing each other. And it's just adding up a whole bunch of these things. But in every case, there's equal and opposite forces going on. And so they all add up to one big equal and opposite force. We don't try to analyze it down to the atomic level. We just look at the resultant force of all those things acting on the bottom of the coffee cup, and then the coffee cup acting on all those things in the tabletop. So that's what we have. And that reminded me I'm thirsty. So it's a water cup right now. So that's Newton's third law of motion. One more example for today. Let's suppose that we've got the Earth down here, and we have a student from Big Bend who is taking skydiving lessons and gets to do their first jump out of an airplane. And so this person, they've got their arms spread out, and let's see, I guess their legs will kind of look like that. I can't draw worth beans. And we better give them a parachute just for the heck of it. So there's their parachute. And we can look at this and think, okay, what force is acting on this skydiver that makes them move toward the ground? And that force would be the force of the Earth pulling down on them. So we can draw an arrow for that and label it. Down on Skydiver. Running out of room. Okay, what is the third law partner of that force? Well, here's the way I figure it out. I look, what is exerting this force? The Earth is exerting that force. What is the force acting on? It's acting on the skydiver. So here's my object 1, here's my object 2. I swap them to figure out the third law partner of this force. And we tend to call these things third law partners or third law pairs. So what I'll get is the force of the skydiver. This is going to sound ridiculous, by the way. I do want to reverse the direction of the force. So pulling up on Earth. Now, this force happens to be the gravitational force, okay? And so does this force. There's a gravitational attraction between the skydiver and the Earth, and so this force is going to be acting basically on the center of the Earth when you add it all together to this thing. And these are the two third law partners. Well, why don't they meet halfway between then? Because if this was the case, it would be sort of weird. If the skydiver is accelerating downward toward the Earth at 9.81 meters per second squared, and the Earth accelerated upward at 9.81 meters per second squared, you might spill your breakfast cereal or something like that with the Earth accelerating up like that. Or if somebody on the side of the Earth over here was skydiving. But the forces may be equal, but their results are not. And that's because the acceleration of an object is the net force acting on them divided by their mass. Now, the skydiver doesn't have that big of a mass, but the Earth does. And so this is the acceleration of the skydiver. The acceleration of the Earth, AAR, close enough, is going to be the same amount of net force, but what goes on here is the mass of the Earth, which is about roughly 10 to the 22nd times as big as the mass of the skydiver, which means their acceleration is going to be 10 to the 22nd times bigger than the acceleration of the Earth, which means the Earth doesn't go anywhere. Okay. Now, every once in a while, something bigger will exert a force on the Earth, like, say, the moon, and then the force that the moon exerts on the Earth actually does have a noticeable effect on the Earth. And so tides for one, but there are other ones that we'll talk about later. Well, we're about out of time for today. We'll be studying Newton's laws and its effects here for this entire unit. The next unit that we'll have a test on is only on chapters 4 and 5, and all of it deals with Newton's laws of motion and applying them to various problems. And so that's what we'll get good at. Eventually, we're going to start adding angles to the mix and adding friction to the mix and lots of different things. But we're getting there anyway. And be watching probably by late this afternoon. I should be able to have that projectile motion lab posted. I have to head out to school here for a little while today for a couple of astronomy students who had problems with the test yesterday. Their internet crashed at home, and this teaching online is complicated. But anyway, we'll deal with that then. Okay, so dive in. There is a new sapling assignment, so start having a look at those things. Reading the chapter on Chapter 4 is what we're starting right now in a few seconds.
Do you know when the lab is going to be posted?
By 5-ish tonight, I think.
Okay.
Yeah.
And then, like the other thing, so the lecture yesterday that you gave, are you going to post that too? Or?
Yeah, I forgot to put it up there, but I did. It has been processed. I just need to post or get those up to YouTube, and YouTube has to process them, and then they scan them to make sure there's nothing in them that is copyrighted. This is kind of interesting. For one lab last quarter, I made a video out at school of the part of the experiment, and when I first started recording the video, I realized I hadn't shut off the thing I was playing music through my phone on, And so I had to walk across the room and shut it off. And it caught about 5 seconds of this song. And when I tried to post that video to YouTube, it said there was a copyright violation, that I was trying to post a song that was copyrighted for just 5 seconds of it. And somehow it recognized the song from the 5 seconds or so that it worked. So I had to, you can actually edit it on YouTube. I had to cut out those first few seconds of the recording before they would let me post it. It's just kind of ridiculous, but some people do try to make money off other people's work, so that's why. But I'll get that. I should have that stuff posted by noon, I think, or maybe 12:15 at the latest. So, all righty.
Is it going to be due on like at the same time, or is it like an extension now? Because it's
say that again.
Is it going to be due at the same time, or is there going to be like an extension?
The lab?
Yeah.
Oh, it'll be due next week.
Okay.
Yeah. So it's this week's lab, but it'll be due next week. So yeah, I think I'll set it up so you'll have probably next Wednesday would be as good a day as any. Should work anyway. Okay. Well, I'm gonna end this and get that stuff posted as quick as I can.